Okay, let's integrate f of x comma y comma z equals z over the region E, where E is the solid tetrahedron formed by or enclosed by the four planes. And here they are, x equals 0, and y equals 0, and z equals 0. Okay, those planes are all easy enough to deal with. And the plane 2x plus 3y plus 5z is equal to 30. So this the fourth and final plane has to be a little more interesting. It has a normal vector of 2, 3, 5. Let's just draw a picture. I'm not going to draw the plane x equals 0, y equals 0, z equals 0. I'll just first draw in some axes. So all the coordinate parallel planes, that's fine, right? So there's a plane that goes through the y and z axis and like completely contains both the y-axis and z-axis, and that's the plane x equals 0, for instance. What I want to do is talk about this last plane, and the easiest way to talk about it is what's the x-intercept, y-intercept, and z-intercept. And to find the x-intercept, you set y and z equal to 0, so you have 2x is equal to 30. You end up with 15. Same deal when you go through and you plug in x and z are 0, then you get 3y equals 30, so you get 10 as the y-intercept, and similarly you'll get 6 as the z-intercept. The point is, there's the origin back here, and it's the tetrahedron. You know, it's a pyramid that every side of every way you look at the pyramid, there will be a triangle of some kind. It won't always be a right triangle, and or if you want to call it this way, is look at this plane, and then if the origin is the corner of the room, like let's say you set this cardboard triangle in the corner of a room, and all the points that are hidden by the cardboard, that would form the tetrahedron. So we'll just comment here that E has vertices 0, 0, 0, 15, 0, 0, 0, 10, 0, and 0, 0, 6. So let's write this. We've just got to choose an order. So we'll do an integral from something to something, an integral from something to something, an integral from something to something, and the function f, we were told, we'll just put an f here for now. Let's just go with this order: dz as the inner integral, then dy, then dx. Now, here's the thing. How do we figure out the z? Well, that one's actually not so bad because we have z0, and then we could solve for z here. Yeah, so like no matter what x and y you're at, here z starts at 0, yeah, and then increases up until the point where it ends up hitting a point that's on this triangle, on that upper triangle there. Okay, so z here, you know, z goes from, let's say from g sub 1 of xy to g sub 2 of xy. Now both could be functions, but in this case this function is just 0, and g sub 2, we just need to solve for z over there, and so you get 30 minus 2x minus 3y all over 5. Okay, now what about, so that will set up these two here, okay, but then what do we do about setting up the bounds for y and z, right? So bounds here, this gets a little challenging, but it takes some work, and the key thing to do, the book's language is to project onto the xy plane. So what I'd like to say about this, because this language project might sound strange to you at first, but imagine that you're a bird, you know, way up where the z-axis is positive, go way up there, right? And if you look down, you know, if you're the bird, I don't care if you're a little bit this way or a little that way, you know, a little to the left, a little to the right, just go way up high, and then look down at what you have, and you should see the following shape. So if you're a bird, you look down and you'll still see this x-intercept of 15 and this y-intercept of 10. So you're going to see, let me draw that a little better. You're going to see this triangle. So in other words, go way up there and almost lose your depth perception, right? Just kind of like hold one eye closed and look at what shape you'd see from above, and it would look like this. Okay, so let's talk about what this line here looks like. An equation for this tilted line here, right, is 2x plus 3y is equal to 30, right? You can work that out. Okay, and so then we're trying to work on, say the y bounds here, right? So what we'll do is at the small, so for a typical x value, maybe like right here is a typical x value, y starts at 0, but y ends at its largest on this line. So the y bounds here, so y goes from it goes from 0 all the way up to, well, got to solve for y there. So all the way up to 30 minus 2x over 3. Yeah, so if we write this integral here a little better, now we have still something, we're not sure, but integral from 0 to 30 minus 2x all over 3. And then we saw the z go from 0 to 30 minus 2x minus 3y over 5. And let's go ahead and replace f. It was f of x comma y comma z. In this example was the function z, dz, dy, dx. I guess why not? And then what left for the x values? Well, that's just the largest and smallest x values that you see, but I'm going to actually suggest, just to make the process consistent, let's project onto the x-axis, meaning, so say you're a bird and you're now going to be way up here. There's where the bird is located, and when you look down at this shape and all you see is this flat, ground here, what you're going to see is just this part here. So as a picture on the x-axis, you're going to see 0, 15, and you'll see this, right? So then that is what's going to end up over here. So x goes between 0 and 15, and so we'll have that this integral is really 0 to 15, integral 0 to 30 minus 2x over 3, integral 0 to 30 minus 2x minus 3y over 5 of the function z, dz, dy, dx. I mean, the function was f, but its value was z. So what I'll suggest you try to do, this is very challenging to do at first, but what I'd suggest you do is to try setting up all 6 on your own. So something of the form integral something to something, integral something to something, integral something to something of the function. It doesn't actually really matter what the function is right here, right? But maybe try, for instance, like a dx, dy, dz as well. This would be another one to try. So figure out x goes from a function that is in terms of y and z to, at the largest, a value in terms of y and z again, and then to figure out the y and z bounds, then you project onto the y-z plane, and on it goes like that. So try it. Do all 6. Got to catch them all.